So how can you find the domain of a function? Consider this function f of x equals 3x minus 4. What are the least of all possible value of x that can make this function to still be a real number? Now you need to keep in mind that your domain that you are to list out must be values that will always keep on being or allowing your function to still be a real numbers. And that's your main goal. In calculus, we must never have an undefined function, likewise imaginary numbers. So your main goal is to avoid having an undefined value or undefined function or an imaginary value. You must keep on having a real numbers. So it turns out that whenever you are having a linear function, just like this, the possible values that can keep on being or allowing this to still be a real numbers is from negative infinity all the way to positive infinity. Now, there are two different brackets that you need to be familiar with. The first one is called parenthesis, while the second one is called close bracket. We use this for interval, whereby the values that are within it are being included in that problem. So if this is used to describe value, then that value won't be included if it's an interval notation. Like what I'm saying in essence is that if I have a number line, let's say I have two test points or two critical points, let's say 3 and 2. Now, if at all it's an inequality, if 3 is among the solution, then I'm going to shade it. And if 2 is not among the solution, then I'm going to leave it open. Now, to represent this using these two brackets, is what you need to do. So let me just use the region between 3 and 2 only. And I'm going to use the closing bracket in the first place, showing that it includes 3, but the parenthesis in the last place, showing that it doesn't include 2. So that's what it means. So if a value is associated with this close bracket, it means that value is among. While if value is not is associated with this parenthesis, it means the value is not among. So make sure you keep that in mind as we are going to be using it as we proceed forward in this video. So let's go over more examples on how to find the domain of a function. Now, what about this function? What could be the possible value of x that can make it to still be a real number? Let's say you have f of x to be indeed equals to x squared plus 1. What are the possible value of x that can make this to still be a real number? So this is a quadratic function. So if you're having a quadratic function, unlike that of linear function, its possible values is still going to be from negative infinity all the way to positive infinity. So the domain in this case is still from negative infinity, then all the way to infinity, which is positive infinity. All possible values between these two range can always keep this in real numbers. Now, what about this? What would you say? Try to pause the video and check this question out. This is a rational function, and whenever you're having a rational function, you need to be very careful. Your main goal is to focus on the denominator. Sometimes we will need to consider the numerator as well, but in that case, I will let you know. A case whereby you need to consider both the numerator and the denominator. But for a problem like this, whereby the numerator is consisting of linear function, unlike 2 plus 1, then you don't need to bother about that. Just focus on the denominator. So your main goal is to set the denominator not to be equals to 0. Because when the denominator is equals to 0, then that function will be undefined. It knows that whenever anything is divided by 0, that thing is going to be undefined. But our main goal in this topic is not to make any function to be undefined. So whatever value that's going to make that function to be undefined must not be among the domain of that function. So let's say 2 minus x is not equals to 0. So it means the value of x, if I should bring x to this side, okay, It means the value of x is not equals to 2. So therefore, the domain is going to ranges from negative infinity all the way to 2, then union starting from 2 all the way to positive infinity. So this could be the domain of this rational function, meaning that it can be any possible value from negative infinity all the way to 2, but it won't include 2, meaning that it must not be equal to 2. You know, if I should put it this way, negative infinity, comma 2, then I close it. It means in this case, it will include 2. But I'm not using a closing bracket, but the parentheses, which makes it to be perfect. So this is the domain of this problem. Now, what about this? Try to pause the video and check this question out. Now, it turns out that we are still having a linear function at the numerator. So we keep that aside and focus on the denominator. So we are having a quadratic function at the denominator, and our main goal is to set it not to be equals to 0. Okay, this expression must not equal to 0, otherwise that function is going to be undefined. So the next thing we want to do is just to solve for the possible value of x. So since this is a difference of two squares, I'm going to break it down in pieces as this: x minus 1, then x plus 1. I believe he knows that. He knows that if you have a squared minus b squared, that's simply the same as a minus b, then multiplied by a plus b. So that's exactly what I'm trying to use over here. And I'm going to set that to be equal to 0. Then finally, the value of x can be 1 or it can be negative 1. Then my conclusion is that the domain is going to become ranges of value from negative infinity all the way to negative 1, but not including 1, union 1 all the way to positive infinity, but not including the 1. So this is how it's going to be, okay? If you are wondering about the union, meaning that like the combination, I believe you were taught union in your first year, so you should be able to understand what that means, okay? The combination of both the elements in both of them. That's what it means, okay? And if you don't want to use this, there's another way in which you can represent this. You can just set the possible value of x include x to be less than 1 and x to be greater than 1, and x is less than minus 1. So you can put it in inequality form like this, but this is how it is often written, so you need to make sure you work with this in all cases. So let's try to go over plenty more problems so as to develop your ability in this topic. So try to pause the video and check this question out. So here it is. It turns out that for the numerator, we are still having a linear function, and at the denominator, we are having a quadratic function. So the first thing we'd like to do is to set the denominator not to be equal to 0. So therefore, x squared plus x negative 6 must not be equal to 0. Otherwise, the function will become an undefined function. Excuse me. Then the next thing we would like to do is to factorize this quadratic function in order to get the two critical points. So what two numbers multiply to negative 6 and add up to positive 1? So that should be negative 2 and positive 3. So what I'm trying to do is that I need two numbers that multiply to negative 6, that's positive 2 or positive 3, positive 3 and negative 2. And at the same time, their sum becomes positive 1. It turns out that positive 3 and negative 2 works. So I'm going to replace the middle term with this over here. Then I'm going to have x squared plus 3x, then minus 2x, minus 6 to be equal to 0. So this is still what we have over here. Then I'll just factorize x. I have x plus 3. Then I will factorize negative 2 over here. Then I have negative 2 in the bracket of x plus 3. then finally not to be equals to 0. Okay, then finally x minus 2, x plus 3 is not going to be 0, and x is not going to be 2, and x is not going to be negative 3. So these are the two possible values that x can never be. So with this, we can write the interval notation of the inequality. So, sorry, of the function rather. If you want to write it in inequality form, you can just set that x is less than negative 3 or x is greater than 2. This is accepted. And if you want to put it in the interval notation, you can begin from negative infinity all the way to negative 3, but it won't include negative 3. Union, you open a bracket, typically a parenthesis, starting from 2, then all the way to positive infinity. It won't include the 2. So these two are absolutely correct. So let's try more. But radical function this time around, I mean square root functions, because that's what usually seems confusing to many students. So let's say I have the square root of x minus 4. How can I find the possible value that x can be? Now you need to keep in mind that there's something we call complex number. We have complex number when we have the square root of negative value. So your main goal is to have, or is not to have, negative value in the within the radical. So whenever you are having square root function and you are asked to find the domain, so what you are going to do is to set whatever you are having within the radical to be greater than or equal to 0. With that, we won't have a complex number. Once it is less than 0, it means it has become a negative value. And once it's a negative value, it's going to become a complex number. So that's your main goal. So I'll just take x minus 4 and set it to be greater than or equals to 0. With this, whatever is going to be is still going to be a real number. Then I'm going to solve for x, as x is going to be greater than or equals to positive 4. And this is the value of x. And to put that in the interval notation, this is your solution anyway in inequality form. So you can put it in interval notation as well by saying that the domain is simply equals to 4. Since it's going to include 4, we are using a close bracket over here. Okay, it's gonna be equals to 4, and all the way to positive infinity. Then you put parentheses. I believe you grab the concepts now. Let's try more, so you can see the beauty behind this aspect. So let's say I have the square root of a quadratic function now, x squared, then plus 3x minus 28. How can we find the domain of this kind of function? So what we are going to do in this case is that, unlike before, you are just going to set what you have within the radical to be greater than or equals to 0. So I have x squared plus 3x minus 28 to be greater than or equals to 0. My main goal right now is to factorize this trinomial. So what two numbers multiply to negative 28 and add up to positive 3? So what could that be? Think about it. It turns out that positive 7 and negative 4 are the two best values. So it's going to be positive 7 and negative 4. So if I should add this up, I should have positive 3. And if I should multiply them, I should have negative 28. So I'm just going to replace the middle term with this and this. So let's go. So I'm going to have x squared plus 7x minus 4x minus 28 to be greater than or equals to 0. Then I'm going to factorize at this point. So let me take the GCF. So I have x to be common for this part. I'm trying to group it. Then I have x plus 7 left over. Then I'm going to take negative 4 as a common factor over here. And I have x plus 7 left over. Everything is greater than 0. Then finally, I'm going to take out the GCF. I'm just going to compare the bracket and have x minus 4 then being associated with x plus 7. Then everything is greater than or equals to 0. Then finally, x is greater than or equals to 4, and x is greater than or equals to negative 7. Now, there's something you will need to do. Please and please, I will want you to keep this at the back of your mind. Whenever you are having a radical function, such that within the function you are having a quadratic function, after getting the two critical points, please, you need to use what we call a point test. Okay, we call it a point test. We use a number line to test if that statement is going to remain the same. We want to test the region that keeps on giving us value that is greater than 0. So how can we do that? The first thing you want to do is just to draw a number line. Draw a straight line. Then you plug in the 2 points you have, 4 and -7. So let's say all the way to the left I have negative infinity, all the way to the right I have positive infinity. Then closer to negative infinity I will have -7. Then closer to positive infinity I will have +4. So this region is between negative infinity and -7, while this region is between -7 and +4, and the last region is between 4 and positive infinity. It turns out that not all this region, it keeps on giving us values that is greater than 0, which is the main reason why we need to do the test. So how can we go ahead and doing the test? We want to select a value within 4 and 8 within this region. Now we are going to plug it in this factorization form. So if the result tends to be greater than 0, then we can go ahead and consider the region. Otherwise, it must be eliminated. So let's consider 5. 5 is between 4 and positive infinity. If I plug in 5 here, 5 minus 4, that's positive 1, and 5 plus 7, that's positive. Positive times positive is simply positive, and any positive value is always greater than 0. So therefore, I have positive value here. Now, I need a value between this region, between 7 and -4, between -7 and 4. So I would like to use 0. It turns out that 0 minus 4 is simply -4, and 0 plus 7 is simply 7. Negative multiplied by positive will result in negative. But it turns out that negative value is not greater than 0. So this point right here is negative. Now, one good thing about number line is that if one region is positive and the second region is negative, then the third region is going to alternate. It's going to be the opposite of the previous region. So which implies that this point is going to be positive. But let's confirm it by plugging in a particular value. So I want to get a value within negative infinity and -7. So I would like to use -8. -8 minus 4, that's -12. -8 plus 7, that's -1. Negative times negative, that's simply positive. And positive value is more than 0. So therefore, we have it here. Now, if you could recall, our main goal is to get value that is greater than 0. Otherwise, we are going to have an imaginary number, and we don't want to have that. So therefore, we are going to consider these two regions. Can you now see the function of the test point? So therefore, the domain is going to become negative infinity all the way to -7, which won't include okay, it will include -7. It will include 7 because it is greater than or equals to, we are going to shade the region. We are going to shade the region and union. So I'm going to use a close bracket. Okay, I close it over here. So I'm going to shade this region since it is greater than or equals to. You understand? Meaning that it's including it. Union, then it's also including 4 all the way to positive infinity. And I'm going to use the parentheses. And this is my domain for this function as well. So that's it. Now, what about this one? What would you do? Try to pause the video and figure this question out. What if we are having a rational function that is having a square root function as the denominator? This is what I'm saying makes sense. How can we find the domain of this function? You know, if you could recall, I said when it comes to rational function, your main goal is to check what you have at the numerator and also what you have at the denominator. If what you have at the numerator is a linear function, forget about it and focus on what you have at the denominator. It turns out that what we are having at the numerator here is just a linear function. I'm going to leave that aside and focus on the denominator. The question you might want to ask is that why are we ignoring the linear function that's at the numerator? The reason is all because whenever we are having a linear function, its domain is all real numbers from negative infinity all the way to positive infinity. Our main goal is to focus on the one that might have some values not to be included. So whenever you are having square root number, I said you need to set what you have within the radical or you have within the square root to be greater than or equals to 0. But unfortunately, when we're having a rational function, we can't set the denominator to be 0. Otherwise, the function is going to be undefined. So therefore, instead of saying x plus 3 is greater than or equals to 0, we are just going to say x plus 3 is greater than 0. Please be mindful of this. This is very important. When you are having a square root to be standing alone, then it must be set to be greater than or equals to 0. But when that square root is serving as a denominator of a particular function, then it must be greater than 0 only. It must not be equal to 0. Otherwise, it's going to be a undefined function. So that is the reason why we just need to set it to be greater than 0 only. So with that, I can just solve for x by saying x is greater than negative 3. So with that, I can get domain. So the domain is just going to be from negative 3 and all the way to positive infinity. So this is the domain of this particular function. I believe you grabbed that. So let's move on. Let's consider another one. Let's consider a situation whereby the domain or the radical function is at the numerator. So try this one out. Okay, pause the video and figure this question out. So if you have a function that is equals to this, what would you do? Now it turns out that we are having a radical function at the numerator and we are having a quadratic function at the denominator. It means we are to consider both the numerator and the denominator in this case. You get the point. If at all the numerator is a linear function, we don't have to consider it. But right now, it is a radical function. If the numerator is a quadratic function, you don't bother to consider it, okay? Because quadratic function that is serving as a numerator will still keeps on being from negative infinity all the way to positive infinity. It's just that when it is serving as denominator, that is when it will have condition that you need to solve for. It will not be equal to 0 in that case. So I'm just going to focus on both of them one after the other. For the numerator, I have square root of x minus 4. Then I'm going to set that to be greater than or equals to 0. You understand? That's more than 0. Otherwise, okay, I'm referring to x minus 4 only, not square root of x minus 4. So greater than or equal to 0. Then the second one, that's x squared minus 25. That must be not equals to 0. Okay, since this is not a square root function, you don't need to use the inequality. It's just an ordinary quadratic function, so it must not be equal to 0. So for this, I'm going to solve for x. So x is going to be greater than or equals to positive 4. Why for this, I'm going to factorize first, since it is the difference of two squares. So I'm going to have x minus 5, then x plus 5 to not be equals to 0. So x must not be equals to 5 and x must not be equals to negative 5. So with this, I will need to use a line test. I'm going to use a test point to know where to select as the region. Don't forget, I said whenever you are having a quadratic function as the denominator, you must always use the test point to confirm where to select as your acceptable region. So I'm going to have my number line over here. So I have negative infinity all the way to the left. I have positive infinity all the way to the right. So somewhere closer to negative infinity, I have negative 5. Then after that, I have positive 4, which is this. Then which follows which positive 5 follows. So it turns out that there's no solution, there's no reason for selecting any value over it. Okay, this will not work because it won't work for the upper one. X must not be less than 4. Okay, it must be greater than 4 or equals to 4. If x is less than 4, then that numerator will become an imaginary number. That is why we won't even select anything within this region. You get my point? So we need to consider both cases here. If the denominator works, if we select minus 5, or let's say minus 6, okay, so we select minus 6. If I should plug in minus 6 at the denominator will become 36 minus 25. That's simply 11. But for the numerator, it's going to become minus 6 minus 4. That's minus 10. That's square root of minus 10, which has become an imaginary number. But that's exactly what I'm trying to avoid. So there's no reason, there's no solution in selecting any point within this region. So that has been ignored. So we are going to focus on these two regions right here. We're going to focus on the region between 5 and 4 and 5 and positive infinity. Since x can be equals to 4, then it means we must consider this region from 4 to 5. So it's going to be, the domain is going to become this way, starting from 4, then it won't include 5. Then union, starting from 5, not including 5, all the way to positive infinity. So this will be the set of the domain. You can see it's still the same thing as this inequality form. You can just set that x is greater than or equals to 4, okay, and x is greater than 5, okay, but x is not equal to 5 here. You can just say but not 5. You understand? It must not be equals to 5. So that's just how it's going to be using the inequality form. So let's try the last example, which we are going to use to stop this video. By now, you should have familiar with how to find the domain of a function. If you haven't subscribed to this channel, please do well to subscribe now. Thanks for watching. I really appreciate. So let's consider a situation whereby we are having radicals in both the numerator and the denominator. So let's say I have square root of x plus 3. So we're dividing the square root of x squared minus 16. Okay, so just watch carefully and see how I'm going to undo this problem. So since both of them are having radical, we are going to consider the both cases. So for the numerator, x plus 3 must be greater than or equal to 0, while for the denominator, x squared minus 16 must not be equal to 0, but always greater than 0. It will not be negative value as well. Excuse me. So for the first one, the value of x is going to be greater than or equals to 3. While for the second one, I would like to factorize first. So I have x squared, x minus 4, that's difference of two squares, and x plus 4 to be greater than 0. Then I have x to be greater than 4, and x is greater than negative 4. Now at this point, I will use the number line to test those points. Okay, so negative infinity, then positive infinity. Then I have negative 4, and I have positive 4. So that's for this one. Then I will draw the number line for this one as well. So that's it over here. So I have negative infinity, positive infinity. Then I have 3 somewhere around here. So since it is including 3 and is going towards the right hand side, or towards the right hand side, then this is where it is heading to. Alright, now let me focus on this. Is there any point that we can select between negative infinity and negative 4? It turns out that whatever point we are going to select must must correspond to both, like it must work for both the numerator and denominator, okay, such that both of them will still be a real number. If I should consider negative 5, which is a point between negative infinity and negative 4, it will turn the numerator to become an imaginary number, even though the numerator can still be a real number. But when I'm having imaginary number dividing a real number, it won't really make sense. You understand? So I'm still going to be having an imaginary number in that case. So um, selecting this region is not of use. There's no point in selecting this region at all. So our main goal is to focus on these two other region. Okay, though this is intact already, we don't have to touch that. We just need to focus on these two other region. Is there point in selecting region between negative 4 and 4? Now, I would like to take a point between negative 4 and 4. I would like to select 0. Plugging in 0 at the numerator and the denominator, will the result still be a real number? It turns out that the numerator will still be a real number because 0 plus 3 is simply 0, is simply 3, and the square root of 3 will give you a value. But unfortunately, for the denominator, I will now have an imaginary number because 0 squared is simply 0, and 0 minus 16 is minus 16. And square root of minus 16 will become an imaginary number. So definitely, this point has already been eliminated too. So my main goal is to focus on this and this. So is there point in selecting this? Yeah, let's consider 5. If I should plug in 5 plus 3, this work, then 5 squared and this work. Since this region work, then we are going to focus on this region. But unfortunately, I think there was a mistake here. It should be negative 3. So that should be negative 3. Because when I bring 3 to this side, it should be negative. So x should be greater than or equals to negative 3. So I will draw another number line to confirm these other two we just left. So I have negative infinity, I have positive infinity, and then closer to negative infinity, I have negative 3. Then what follows is positive 4. So I need to select a region between I already knew that region between negative infinity all the way to negative 3 is eliminated. There's no point in that. What about negative 3 and 4? Negative 3 and 4, I'm going to select 0. Okay, 0 has already been tested over here and it doesn't work anyway. Then I'm just going to eliminate this region and this region. So therefore, the domain will just be equals to 4. Will it be including 4? It turns out that it won't be including 4. So we are using a parenthesis, then all the way to positive infinity, closed by the parenthesis. And this is the domain of this function. So hopefully now you know how to find the domain of a particular function. So what you just need to keep in mind for review is that if you are having a linear function, the domain will always be from negative infinity all the way to positive infinity. And if you are having a quadratic function, it's still going to be from negative infinity all the way to positive infinity. Now, if you're having a rational function, q over p, it depends. If it is just this is linear, if this is linear or quadratic without radical, focus on p. Okay, if p is linear, then you set it not to be equals to 0. If it is quadratic, you set it not to be equals to 0. Then you just select those points as your values that the function won't reach, like the values it won't include. Now, if q over p is having radicals, let's say we just have radicals only first. Let's say I have square root of p. Then in this case, I will just set p to be greater than or equals to 0. Okay, that's a radical function. Then I'll solve for whatever is going to be. Then if it is q square root of, or let's say q over square root of p, then in this case I will just set p to be greater than 0 only. It must not be equals to 0. And if I have square root of q divided by square root of p, then what I will do in this case is that I'm going to set q to be greater than equal to 0 and p to be greater than 0. And I'm going to find a region that work for both the numerator and denominator to keep on being a real number and not a imaginary number or an undefined. So that is it for this video. Thanks for watching. See you guys in the next video. If you haven't subscribed, do well to click the subscribe button and turn on the notification bell so that you won't miss out any update. Thank you.